Seriously?
I don't know what to say. I don't hear it.
Well, whoever else came in after we got started, I have your email up here. Grab it on your way out, people. Ozzy, on your way out.
Yeah, I just stopped listening. I stopped to watch the other group. I'm gonna rewatch this one. For chapter 9.
Oh, yeah. Okay, sample size 5.
I don't know. That's why.
No, because I didn't ask you. Hey, guys, she's asking about that calculation to make sure that you can do a proportion hypothesis testing. That's that calculation where you take the sample size times the hypothesized proportion, and then you also take the sample size times 1 minus the hypothesized proportion. They both have to be true, greater than equal to 5. Both of them have to be true, greater than equal to 5. If you are supposed to do that, in the instructions it will say to make sure, it will tell you to do it. I'm not going to give you this. I'm just telling you. You'll know that you should be doing that or doing something, and then you got to remember that's the thing you're supposed to be doing. The whole reason for doing that is to ensure that you can use the proportion hypothesized testing because it meets that criteria. Both proportions meet it.
Before we start, actually.
Oh.
What? You want to do something else before we start? What is it? Are we good? Start what? The new material? Yeah, it will meet the criteria. It's just a matter of you show me it meets the criteria. Because if it doesn't meet the criteria, then you're not going to do the rest of the problem. And I'm not going to trick you, because you'll see there'll be so many points that I'm looking that it will meet the criteria. I just need to see that you know to do that calculation and how you do it, and that you did both of them to prove they're both true. They both got to be greater than equal to 5. You can't just do one of them.
Are you gonna restart?
Did we start already?
You already started.
Yeah.
Oh, we did? Oh, man. I didn't realize we restarted already. Look, everything's shutting down. All right, let's get to the new stuff. Are we ready? Whoop. Here's week in 7 instructions. Here's the words you love the most. Let me make it bigger. Here's your favorite words right there. When's homework due? You know, that's why I'm going to post the answer tonight, so you can use it as a study tool. All right. There's today's PowerPoint, just a few slides. Number 2 through 11 of a new PowerPoint is called Chapter 10, 11. And then we have some Excels, we have some textbook pages, and then of course I'm recording this to put up. Now, here's the homework. Right here. Let me make it bigger. We are at that point. Everything up to this point has been a building block to this moment. Because now we're going from, before it was confidence intervals only. Then we had a group of 3 weeks where it was hypothesis testing. But it was hypothesis testing a theory against a sample. Now we're all about having 2 samples. 2 samples. And comparing the samples to each other to see if they're statistically different or not. That's where we're at. Now I want to point out something. Look at how many we have to go through. It's going to be the next few weeks here. There's population means independent samples, right? And then there's means that are related, and then there's proportions. This is very much like the 3 different kinds that we had before, but it's a little different. Let me give you an example. So today, we're talking about population means independent samples, but the bad news is there's 3 different equations for population means with independent samples. Here's the good news. To determine which one of these 3 you use, it's the same criteria. You're looking at the problem and you're saying to yourself, do we have the population standard deviation? And if we do, there it is, that top one. This one right there that is going back and forth. Then you're looking at it, hey, we don't have the population standard deviation. Do we have the sample standard deviation? Yes, okay, there it is. Then it's this one or this one. And then if proportion is completely different. But here's the deal, it's the same thing. Now, what you need to get used to is problems are not going to be giving you just the standard deviation in the form of a standard deviation. These problems also are talking about the standard deviation in the form of a variance. But don't let that fool you. You all know a variance is the square of the standard deviation. You all know that the standard deviation is the square root of the variance. Remember, as long as you have that relationship, you don't care if you're reading about a variance or a standard deviation, because you can convert it to one or the other if whatever's needed. In today's formula, the variance is being used. So if you're given the standard deviation of 9, that variance is 81. You may have to calculate. If you're given the calculation, or you're given the variance 81, you don't need to convert it, because the variance is being used. So here's what's happening. We're going to be given samples from 2 independent populations. Let me give you an example. If I said to you, hey, I think the average age of all the females compared to all the males are different from each other. I don't think they're going to be the same average age. I think they're going to be far enough apart to be significantly different. Now, I've just hypothetically made that claim up, but I want you to notice the 2 populations. One population was females, one population was males. I said that's what I'm comparing, and they're independent of each other. No one's in one or the other. I mean, we're not going to get into that debate, but you know what I mean. They're completely 2 different. If I went and said, okay, I'm going to go look, I want to compare this Pepsi to that Coca-Cola. These are 2 different brands. Yes, they're both cola, but they're 2 different brands from 2 different populations. I would sample nothing but Pepsis over here. I'd sample nothing but Coca-Cola over here to compare. Maybe I'm comparing the weight that's in a 2-liter to see how that, hey, we think Pepsi's shorting us. And we're going to compare a sample of 32 liters of Pepsi compared to a sample of 32 liters of Coke, and we're claiming that the Pepsi's going to be significantly less liquid in there. Something like that, but that's what this is all about today, is these are independent samples with population standard deviations known, given to you in the form of a standard deviation or in the form of variance. That's where we're at. Then next week we're going to go to where they're unknown. So now, since we're talking about just one part of this, it's all how you recognize this problem. This is the only type of a problem that has 2 different means that you're comparing. We have not learned that up to this point. Everything since the first quiz to this quiz has been hypothesis testing with 1 mean. But now we're getting into 2 means. And yes, there could be 1 question or 2 questions related to today's lecture about 2 means. And you'll realize it has to do with today's lecture because there's 2 means involved. Now, I want you to think about this. You ready? If there were no difference between the average age of females and the average age of males in this room, no difference, and I took the average age and subtracted them from each other, and they're exactly the same, and I subtract them, what would be the result? 0. You get it? So that's why every one of these are subtracting the 2 means from each other, because the closer to 0 this result is, the closer is that there is no difference between them. The farther away from 0 this is, the more evidence you have that these 2 are significantly different from each other. That's what this is all about. Are our 2 samples different, or are they 2 similar? Do we have, and not only are they different, because look, if I took the average age of females and I took the average age of males, there's no way the 2 answers would be exact, especially if we're going like 2 digits to the right of the decimal. They won't be exact. But are they different enough to have significance, to say they are different from each other? Or are they just a little different from each other? And that's what you're proving with these formulas. This is to get the test statistic. I'll read it out loud. 1 sample mean minus the other divided by, all of this is square rooted. The variance from the first the variance of the first population divided by the sample size of the first sample, plus the variance of the second population divided by the sample size of the second sample. Add those 2 divisions together, square root that, then divide it into this subtraction. That is your Z test statistic. That is what you'll use to find your p-value. And then everything's just like we've learned up to this point. You find your p-value, you compare it to significance. Same exact thing we've learned. Everything you learned is going to be the same way it is again, except the only difference is now we're going to have 2 means. For the next 3 weeks, it's all about 2 means. Crazy, huh? So it's not going to be as hard as you think. Now, here's the critical, confidence interval approach right here. Formula's almost the same, except we have the critical Z here. Here's what's weird. Remember when we were doing proportions? How you gotta have the hypothesized proportion when you get the test statistic, but you use the sample proportion when you're doing the confidence interval? Not in this case. In this case, this variance is the same whether you're doing confidence interval or whether you're doing the test statistic. That variance you used above is also used here. Same variance. So the only difference between finding your test statistic and the critical value is you're adding this multiplication of the critical Z times that square root of everything. The same square root of everything up there. The variance of x1 over the sample of x1 and so on. No, yeah, we're not doing that divide. We're adding and subtracting instead to find the interval. And then, you ready? Your question when you do confidence interval is, did 0 fit? Let me repeat that, because if when you subtract these two and there's no difference between them, the answer would be 0. So when you get your confidence interval, you're going to say, does 0 fit? And if 0 does fit, you can't reject. But if 0 doesn't fit, you have evidence to reject. There's confidence interval. So now, let's talk about this. Where is it? Where's the formula? Just pass it. There. Here's the formula. All, yeah, like the number 0.
Okay.
Here's the formula. All I did was take that and just make it 0. That's all. All I'm doing is just this, because this is always 0. We're saying if there's no difference between them, this would always be 0. So this would be 0. It's almost, I don't want you to get confused and write this down. Use the formula I got up there, which is just getting rid of this whole part to the right in the numerator. The variance, see how it's the standard deviation squared? That means variance. Standard deviation squared means variance. That symbol means population divided by sample size, square root the whole thing. There's how you get your test statistic. Once you have that Z, you treat it just like we've been doing for the last 6 weeks. Now here's the confidence interval formula. Exactly what we have here. One sample minus the other, plus and minus that critical Z. This is critical Z, not your Z statistic. Critical Z, just like every confidence interval. And then the variance over the sample size, variance over the sample size, square root. Don't forget, that square just means that that's the standard deviation squared. It's the variance. You're not squaring anything if you're given the variance. You only if you're given the standard deviation, then do you have to square it. Everybody with me? Go ahead.
Repeat that thing you said, if zero fits, you reject?
If the 0 fits, you know, I could be losing my mind.
You said you can't reject the.
If the 0 fits, you cannot reject. Yeah, but I could be losing my mind. We're going to do an example to see if that's correct or not. You get old, you forget things. All right, so then next week, here's where we're going next week. The two population standard deviations are unknown, meaning you have the sample standard deviations. That's where we're going next week, right there. And we'll go on from there. And look at this formula. This is your T formula for next week. There's the T. But let's stay at the Z. We're on this Z. There's your confidence interval. And there is your Z. Now, here's the different types. When you read a problem, you're going to look at it and you're going to say, okay, are we trying to prove that one mean is less than the other mean? If so, yes, this would be your alternative, this would be your null, but you have to set these to 0. So it means 1 minus the other is greater than or equal to 0, 1 minus the other is less than 0. Because if one is less than the other, the separation when you subtract them would be so far away from 0 that it would be less than 0. Get it? Let's look at this one. This one you're saying, hey, the sample 1 is greater than sample 2. Okay, well then the opposite would be less than equal. But here's the deal, when you subtract the 2, it means that the difference between them will be much greater than 0. So we're converting the wording of how you're going to look at it and go, oh, this says, the manager's saying that sample 1 is going to end up being much larger than sample 2. We're taking those words, writing this out like this, but then this is truly the hypothesis, null hypothesis, and the alternative hypothesis. again, notice the equal sign, no matter which one of these, is always with the null. Also notice, when you're comparing two means, they're always represented by a 0. Everybody see that? 0, 0, 0, 0, 0, 0. It's just a matter of, by subtracting them, is it far less than 0? Is it far greater than 0? Or is it far different from 0? This is two tail, one tail, but using two different means. It's very similar to what we learned. So don't get too confused because it's so similar. We ready for an example? I want to jump to an example. Where's my first example? Right here. Wait, oh, hey, up. Go ahead. Which one? What was what?
It doesn't fit if I didn't.
Oh, here, confidence interval.
Oh.
This confidence interval, you're going to get an upper and lower interval, and then you're comparing 0. See how every one of these hypotheses will have 0? You're trying to see if that 0 fits in the confidence interval or not. And if the 0 fits between the two numbers, you cannot reject.
So we're comparing a 0 instead of like a.
Yeah, instead of like 80% or 12.5, you're comparing 0 in the confidence interval in this case. When you have two means involved, it's all about the 0.
Wait, what about the first one?
The first one is how you're going to find like your p-value
And critical?
and critical and compare critical value approach. You compare that to your critical value. Yes. We're going to do a problem, and we're going to do it all three approaches if it's two-tailed, two approaches if it's only one tail. And then if we have time, I want to jump to the homework problem and do that. All right, so let's do this first example. I'm going to page 349 towards the bottom of your page. Hang on, where is it? Right here. Example 10.3 on page 349. Here's our first example. Again, you know this problem is going to give you the population standard deviations because that's all we're learning this week, is when you're given the population standard deviations. Also ask yourself, are both of these means, or both of these samples coming from independent populations, meaning the populations are not, can't cross over, they're so different from each other. An economist claims that the average weekly food expenditures for households in City 1, here's the two populations. One is City 1, the other one's City 2. No one lives in both cities at the same time. They're completely different from each other, so the samples are coming from two different cities, two different populations. The reason I'm pointing this out is because the next quiz, you got to recognize which one of these to use. You're going, oh, there's two means, but is this, is this a T? Is this a Z? Is this a proportion? Is this a mean? It's going to get harder on quiz 3 because you got two means involved. So in this case, we have two populations, one City 1, one City 2. If both of these samples were coming out of City 1, that's called related samples, related populations. That's going to be in a couple of weeks. This is where this is all heading, and you got to be able to read these and know which one is this. Are these independent? Are these related? These are independent because one's coming from City 1, and it says, now here's the words, the average food expenditures from households in City 1 is more than the average weekly food expenditures for households in City 2. Let's go right there. City 1 has more than City 2. So that would be like this. City 1 more than City 2 is what we're trying to prove. So to write the alternative, the mean from City 1 minus the mean from City 2 is going to be greater than 0. There's your alternative hypothesis based on that statement. Let me go back. So, boy, I better check and see if I'm right. I have a few questions. Let's look in. Where is it? There it is. That the mean, the sample mean from one city minus the mean from the second city is greater than 0. Then the opposite of that, less than equal to 0, would be the null hypothesis. But from that first sentence I read, you can tell that's what we're trying to prove, that the mean from City 1 is greater than, let me read it again. The economist claims that the average weekly food expenditures from households in City 1 is more than the average weekly food expenditures from City 2. She surveys 35 households in City 1. So let's go down here. There's the 35. There's your sample size. This is all about City 1. She samples 35 households from City 1, obtains an average weekly food expenditure of $164. There's our mean for City 1, for the first sample. a sample of 30 households in city 2. So it also 35 households from city 1, 30 from city 2. I like how they're both 30 or above, which is the golden rule I told you about. Don't get me wrong, sometimes you can go less than 30, but the golden rule in real research is always 30 or more in your sample size. And the average weekly food expenditures in city 2 is 159. Notice city 1's average, 164, is greater than 159. But is that difference large enough to be statistically relevant? Or is it just randomness that caused that? That's what we're calculating. We can obviously see one's greater than the other, but it doesn't prove your claim. That could be just, we only took 30 households, so that could make them different from each other. So sure enough, it says prior studies suggest that the population standard deviation, here it is, it's giving you the standard deviation, and it says population. That's how you know this is Z, which is all we're doing before the quiz on Thursday, is just this part of it, so you know it's gonna be Z. And it says city 1 and city 2 were $12.50, $9.25 respectively. There's your stats right there for city 1 and city 2. Now, before I look at the answer here, talk me through this real quick. What number is the first number I'm going to have right here on the left in my numerator? 164 minus what? That's right. Variant. What number's right here in the numerator? Variance 1. Oh, 12.50. What though? Squared. Because it's only the standard deviation. You got to have the variance. You got to square it. And be careful. Sometimes it will give you the variance and you don't square it, and yet you will accidentally square it. So be careful. Read whether it's giving you standard deviation or variance. Okay? That's right. So 12.5 squared over what sample size? 35 plus the variance for number 2, which is what? 9.25 squared divided by what sample size? 30. Square root that whole thing. There you go. Now, we didn't get a significance yet, so we got to read this, and if we go down to C, it says at 5% significance. Let's see what our claim is. Is this a one-tail or two-tail?
One-tail.
One-tail it is. So here we go. Equals, we're doing, what are we doing? I forgot what we're doing. We're doing our test statistic, or are we doing p-value? What are we doing here? Do we need our test statistic to do p-value?
It says both.
All right, just checking. All right, so we get this, we put this all on there, we're gonna get a number. But let's get our p-value without that number real quick. Norm, dot, help me out. Very good. This is the question mark, we don't know, 0, comma 1, comma 1. Whatever this equals, multiply times 2.
No.
One tail, very good. Oh, everybody's gonna ace this. We gotta shorten the time up. Let's vote. Shorten the time up, raise your hand. Not shorten the time up, raise your hand. Thank you, Chris. Thank you, Chris. Boy, there was a majority of people who didn't vote at all, which means I think that means it's okay to raise the time. Wait, am I raising this? Raise it? I meant lower it. You're right. My bad.
How do you know if you're gonna put the 1 minus?
Whether that's positive or negative. We haven't calculated this yet to know whether the 1 minus is in front yet. Good observation. But here, all we gotta know is this right here to know whether we're putting 1 minus in front or not. What number did you tell me was on the left here? 164 minus what? So is it positive or negative?
Positive.
Oh boy, there we go. It's in. There we go. Boom. Wow, I'm teaching you all the shortcuts. 15 minutes means nothing to you now.
How do you know that it's 1-tail?
How do I know it's 1 minus 1?
It's 1-tail.
Oh, we were talking about, yeah, it said that that city 1 has food expenditures more than city 2. And then we looked and we said, oh, it's 1 tail. And we confirmed it. Okay, we're about to get the test statistic. And whatever this ends up being, we plug in right here, and we know it's going to be a positive number. This will give us our p-value, and we do not multiply it times 2, and then we compare it to what? What are we going to compare our p-value to? Which is how much? Significance? 0.05, 5%. Here we go. So we do all the work, we do the calculating. There's our one-tailed null and alternative hypothesis. We do 1.85. Anybody went ahead and tried this, and did they get 1.85? No one tried it? You did, really? Nice. 1.85. We're plugging that in now right here. This is going to be 1.85, and we plug it into Excel. I already did it. I wrote it down. I gotta look at it now. We plugged it in. One tail. I don't have the answer. Dang. Oh, it's right here. What am I saying? And it's 0.0322. 0.0322. We compare that to our significance of 5%. My question for you is reject or not reject? I hear not reject, I hear not reject.
Reject.
I hear reject. I hear reject, that's 2 to 2. We're raising our hand now. This is getting out of control. Our p-value is 0.0322. Our significance is 5%. Reject, raise your hand.
You reject.
Not reject, raise your hand. Reject,
Wait, is our p-value smaller?
Yeah, it's
Reject wins.
Oh, it's reject.
3% is less than 5%, so you must reject. Anytime your p-value is less than your significance, you must reject. Now look, you just took away a good night's sleep for me, because I thought we were gonna ace it.
Now you're gonna add the time.
What'd you say?
I said now you're gonna hire the time.
No. The time's already printed
You
on
said
the
an
quiz. The quiz is printed, already photocopied, the time is already on there, the questions are. You wanna just take it now?
Yeah, get it over.
Is that what she said?
Oh, where's the thing? I don't look at it.
It's right here.
I don't mind taking it right here.
I never leave it anywhere because I'm so afraid someone might have to. You know why I do all the things I do, because
Did I say exam?
I want to take away all temptation of cheating. Once you realize, that nobody else is cheating and it's all a fair playing field, then everybody will put their minds to doing the best they can.
So how come we don't get the full class period to do the quiz?
Yeah.
Well, because I'd have to write so many more questions, and then it would take me so much longer to grade it, then I wouldn't be able to hand it back on Tuesday. You gotta take all that into consideration, customer service. Wait, it's true, what are you talking about? Exactly. And we'll come back up. Well, you put his arm out, you're up.
So the only time we don't compare the significance to that is when we do the.
Critical value or confidence interval instead.
We compare that to the.
Right.
Like the significance we have to compare to that.
No, when you get the confidence interval, you're comparing it to 0, to see if 0 fits or not.
But only for this, right?
Only for confidence interval.
Do it.
But critical value, we're gonna do that right now, everyone. Critical value, help me out. Equals norm dot s dot inv. What number goes right there for critical value for this problem?
0.95.
Wait, what? What? This is the first time I heard it get something wrong. Very, Nicholas, thank you. I appreciate it. I know you're human. All right. No, there's only one tail. We're not using. Look, he caught himself. It's only one tail. We're not
Are we
going to
doing
use the
critical?
other half of the significance. The point, yes, thank you. 0.95. Now, I don't know what the result is, though. No one has Excel open? Oh, I can look here. No, we don't have the critical value. Critical value is not first answer. Anybody? 1.645, 1.96, what is it? 2.11? Seriously, not one person in this room. I know this camera can't see everybody, but there's like 38 people in here, and not one person has Excel open.
1.65.
1.645?
Yeah.
1.645, confirmation, anyone?
Yeah.
Yes, good, there it is. Okay, here we go. You ready? Critical value approach. Critical value approach. Look at your test statistic. Look at your critical value. Is your test statistic closer to 0, or outside, farther away from 0 than your critical value? Inside or outside? I hear two outsides. Anyone else?
Outside.
4
Is
outsides.
greater than.
That's all I got. 4 outsides.
It's-
Okay, here we go.
It's reject.
Is 1.85, look, I just wrote the point up. Outside of 1.645, or is it inside closer to 0? You have evidence to reject. You got it. There's the critical value approach. It's all a matter of knowing the significance to be able to get that number to compare it to what's being calculated there.
Professor, if the z is larger than the critical z, then we just reject, right?
If our z is outside,
You mean
farther
larger?
away from 0 than the critical, we can't reject. We must reject.
So larger, you mean larger, right?
Outside, larger if it's positive, or smaller if it's negative. The reason I'm not using the word smaller and larger, because it depends if you're comparing the negative or the positive. If you're comparing negative, it's smaller. If you're comparing the positive, it's larger. So I use outside, inside, because that word's consistent no matter which side you're using.
So if it was negative and it was outside, would it be like, what would that look like?
Well, if this, she's saying if this is negative 1.5, probably being compared to negative 1.645. It's less than that, but it's really what it is. It's on the outside, farther away from zero. These are both negatives on a number line. Zero is way over here. Then here's negative 1.645. Then outside of that, it's negative 1.85. It's on the outside, you reject.
So fail to reject would be if it was like 1.5.
Yes.
Or negative 1.5.
Negative 1.5 would be inside negative 1.645, and you can't reject. That's right, closer to zero. And it would be larger, and so that's why we can't use the greater than or the less than. Because the negatives is the opposite of the positive. All right, you ready for the critical value approach?
I thought we just did that. We just did that.
Yes, yes. She's asking if the test statistic is what you're comparing to the critical value, and does it have to be on the outside to reject? And the answer is yes, it has to be on the outside to reject. That's right. Now, go ahead. Confidence interval, you want to talk about it?
No.
Okay, what do you want to talk about? Oh, you had your hand up for a minute.
I wasn't stretching.
Oh, okay. Come on, we ready to do confidence interval? Who wants to do confidence interval? Why are you guys not stopping? Wait, here we go.
Wait, what were you trying to compare? Were you trying to see if the zero was in between them?
We aren't on the confidence interval yet, but when we get to the confidence interval, it'd be to see if zero is in between them.
So what did you do for those?
Here, we're comparing the critical value to our test statistic. 1.5 is outside, farther away from zero than 1.645. So since our test statistic's outside the critical value, we reject. Why can't we do confidence interval? Thank you. Why were you stopping me? Were you about to? It's a one tail. Let's get to a two tail. Hang on. Here we go. We got time for this? How are we doing on time? Look at our homework. You ready? So here's the story. Sample mean of x1 is 25. Sample mean of x2 is 29. Population standard deviation of x1 is 9. Population standard deviation of x2 is 8.5. Oh, this sounds familiar. What the heck's going on? Sample size for x1 is 30. Sample size for x2 is 36. Notice, okay, wait a minute. What's our, where's our hypothesis? Hang on. I'm giving you A. Ready? Give the hypothesis, determine whether the population means are different. If the mean for sample 1 minus the mean for sample 2 equals 0, they're not different. That's your null hypothesis. If the mean from sample 1 minus the mean in sample 2 is not equal to 0, that means they are different from each other. So there's the first part. Number 2, construct a 95% confidence interval. We're now doing this right here. Based on, we're going to find the significance, define our critical Z. We're going to get this, multiply them, and add and subtract to that difference to get that confidence interval. Here we go. First, what's our critical Z? Since it's two-tail and we're using 95% confidence interval, we will enter 0.975 because we got to add half the significance because it's two-tail. 1.96 is our critical now. 1.96 is our critical. Let's get our, let's get the whole interval then. Here we go. 25 minus 29 plus or minus 1.96 times 81. Why 81? Because the standard deviation was 9. 9 squared is 81. 8.5 squared, 72.25. I'm converting these to variances. Now I take those variances, divide them by the sample sizes. I do all this math on here. Look at my interval. Are you ready? Let me move it up a little. Whoop, whoop, whoop. Give away the answer. There it is, right by my pointer right now. The interval ends up being negative 8.25 is the lower interval. The upper one is 0.25. Does 0 fit between those two numbers? Think of a number line. I can't hear you guys.
The 0, yeah.
Yes, 0 does. 0 is less than 0.25, but it's greater than negative 8. Zero fits, and because zero fits, you cannot reject. Let's make sure we're right on this. Since the null zero fits in the interval, we cannot reject. That's C. Explain if you can reject or not reject based on the interval calculated. D. Show details calculating your test statistic. Before I show this, help me set it up. You ready? Here's the formula. You can see all the information in this problem right here. 25 minus 29, parentheses, divided by, it's going to be that same thing. The variance, 81 divided by 30 plus 72.25 divided by 36, which is calculated right there. 2.7 plus 2.007. Square root those, you get 4.2523. Well, you know what? Should I check that answer? That looks right. You want to check it though? You ready? I'm going to take 2.7 right there plus 2.007. 2.7 plus 2.007. Then I have to square root it. There's a square root key. Then I have to multiply it times 1.96 times 1.96. Did I get 4.2529? Or 23, excuse me, 4.2523. The answer is yes. So that is right. Zero does fit between them, so that's correct. Just kind of looks weird. D, here's our test statistic. Almost the same calculation. The only difference is we're dividing here instead of using the critical value. We end up getting test statistic of negative 1.84366. Look at this. Negative 1.84, what is it? 84366. There it is. Then it says, once you have your test statistic, E says, explain if you can reject the null hypothesis based on the critical value approach. We did our critical value up here and we got 1.96. Our test statistic is 1.84 plus and minus 1.96. Look at these numbers up here. Our critical value is 1.96 plus and minus. Our test statistic is 1.84366. My question for you is, can you reject or not reject?
You can't reject.
Can't reject, why?
Because zero fits in between.
Because
No,
it
no,
fits.
not because zero fits between, no.
Because it does.
Because the negative 1.84366 is what?
It fits between the numbers.
It's closer to zero inside negative and positive 1.96. It's inside negative 1.96, closer to zero. Have you met?
Yeah.
Darn. I misunderstood you there. I thought you were talking about the confidence interval. Because it's inside the negative 1.96 closer to zero, we cannot reject. That's the critical value. All we have left now is F says, give the Excel equation and calculate the p-value, and G, explain if you can reject the null hypothesis based on that p-value. So before I show it, what numbers are going to go right in here based on what percent significance is this problem? 5, it's 2 tails, so what number is going to go in there?
975.
There it is, 975, because you got to add, I thought Nicholas would go over that one, because you got to add half the significance to the confidence, so there it is. Oh, where's the calculation? Oh, that's still, yeah, outside. Okay, here we go. Norm, DIST, negative 1.8436. We're using no 1 minus in front because we got a negative test statistic. We multiply it times 2 because it's a 2-tail question. It's an equal, not equal to. We get 0.0652. Since p-value 0.0652 is greater than the significance 0.05, we cannot reject. C, we didn't reject. We didn't reject when it was confidence interval because zero fit between them. We did our test statistic compared to 1.96, we couldn't reject. And now that we're looking at our p-value times 2, we can't reject. All 3 of them give you the exact same result, can reject, just 3 different approaches to it. If this is a problem, if this is a problem, right here, if this is a problem on the test, just like this homework, I'm only going to be asking you to do one of the approaches. Either the p-value, the critical value, or the confidence interval approach. One of those 3 is a problem on the test, not all 3 of them in one problem. Everybody with me? Everybody know what to expect? Are we good to go?
No, we have questions.
Do you have anything else you need to do between now and the test in 2 days? Other than study, that's it, right? Yeah, you don't have homework, nothing. Go ahead,
This is
Seth.
going to be posted on.
Yeah, this answer is being posted tonight.
Wait, if we give you the standard deviation, do you square it to get the variance?
Did I square to the variance? I did. I took 9 squared and got 81, and I took the other one, 8.5, right there. Look where my pointer's at, right
So
there.
you just square it?
I squared each of those to get the variance, yeah.
Thanks.
Squared each of those to get the variance. That it? I'm gonna see you in 2 days to take the
Sure.
test.
Can you
That's
give us
it.
an example of a scenario that's gonna be on the quiz? Well, honestly, you've done it before.